Okay, we're going to take a look at a question which involves a conversion of energies: gravitational potential energy, kinetic energy, and elastic potential energy. So the situation is we have a toy car of mass 2 kilograms. It's on a frictionless ramp with a height of 1.23 meters. And at the bottom of the ramp, we have this spring, and the K value is 33.0 newtons per meter. So our question is, we want to know if the car is allowed to roll down the ramp and into this spring bumper, how much is it going to compress the spring? So I've marked this position here as number 1, which is the top of the ramp, and then number 2, which is the bottom of the ramp. So we're going to take a look at the total energy of the system at the top and the bottom, and as we know from conservation of mechanical energy, the energy you start with is the energy you have to finish with. So here are the variables. We have ET, which is total mechanical energy. It's a combination of kinetic energy, energy of motion, EG, which is gravitational potential energy, and EE, which is elastic potential energy. So at number 1, the car is at rest, so there is no kinetic energy, and there is no elastic potential energy. So we're just going to say that that's a 0, and this is also a 0. So the only energy that we have to deal with is gravitational potential energy. And the equation for gravitational potential energy is mass times gravity times height. So let's put in our numbers. So the mass of our object is 2 kilograms. Gravitational acceleration on Earth is 9.8 meters per second squared, and the height the car can drop, which is just the vertical height, is 1.23 meters. If we multiply these out, we get 24.108, and the units will be kilograms, meters squared per second squared, and that is also known as joules. So that means that for this system, with a 2 kilogram car at the top of the ramp, there is a total energy of 24.108 joules. That's the energy we start with, that's the energy we have to finish with. So now we're going to take a look at position number 2, which is at the bottom of the ramp when the car comes into contact with the spring and compresses it. So for the bottom of the ramp, we're just going to list all of the possible energies we could be dealing with: kinetic energy, gravitational potential, and elastic potential. So the way this question is worded, the car will come to rest when the spring is completely compressed, which means there is no kinetic energy and there is no gravitational potential energy, which means that should be a 0. And this should also be a 0. So we're only going to be dealing with elastic potential energy. Now, so total mechanical energy has to be conserved, which means the energy I started with is the energy I have to finish with, which means our 24.108 joules of energy from the top of the ramp have to be equal to the elastic potential energy at the bottom. So 24.108 joules equals 1/2 kx prime squared, and the prime just simply is because this is from the second position. Let's put in our numbers. So 1/2 kx squared, the k is 33.0 newtons per meter, and we want to isolate and solve for x prime squared. So I'm going to divide both sides by 33.0 newtons per meter, which means these will go away. And I will also multiply both sides by 2. So by doing that, we have canceled the k value and the fraction, and then all we're left with is this stuff on the left-hand side. And when we multiply 2 times 24.108 over 33.0, we end up getting 1.46109. So the units we have are joules over newtons per meter. And I will just let you know that because we are doing everything in standard metric units, our displacement for the spring will be in meters. So we have to take the square root of both sides. We end up getting 1.2087 with a whole bunch of 5s. And because our question only had 3 significant digits at the beginning, we can only go to 3 significant digits, which means we have a displacement of the spring of 1.21 meters.